Hello students, this is Kashima Soni and today we are going to take up the examples related to valence bond theory, correct? So before proceeding to the example part, let me just tell you, you have to just go through the previous video that I have uploaded in the valence bond theory series, and that is of postulates, correct? So if you have not gone through the same, I'll mention the link in the description box over here. Go through it, check wisely, only then you'll be able to understand the examples, correct? So let's proceed further. Okay, that we have already discussed in the previous slide. I'll be jumping to the main portion, that is our example. Alright, so if you want me to give you a summarized portion of the postulates of valence bond theory, I'll give it over here. But if you want to revise it in a proper manner, then you have to go and check the link that I have mentioned in the description box, correct? So the postulates of VBT were that your central metal cation or atom, it should have at least that much number of vacant orbital equal to its coordination number in the complex, करेक्ट? तो आपकी जो सेंट्रल मेटल एटम है उसके पास कितने वेकेंट ऑर्बिटल होने चाहिए जितना उसका कोऑर्डिनेशन नंबर है. दैट इज योर फर्स्ट पॉइंट. सेकंड पॉइंट सेज since the maximum angular overlap of two orbital forms the strongest bond, therefore जो आपका vacant orbital होगा वो hybridize करेगा to form a new set of hybrid orbital जिनकी energy atomic orbitals के equal होगी, correct? Okay, then the third point says the bonding in metal complexes arises when a filled ligand like this filled ligand orbital containing lone pair of electron overlap with the vacant hybrid orbital on the metal atom or cation to form a coordinate covalent bond like this, correct? Then using VBT you can find out the magnetic moment, the hybridization, geometry of the complex, its magnetic nature as well, correct? So that is another point. Then we have categorized ligand into two sections, that is strong electron donating ligand and weak highly electronegative ligands like fluorine negative, chloride negative and all that we have taken earlier only. Also your strong ligands have tendency to pair up the d electrons of metal, whereas your weak ligand do not have the tendency to pair up the d electron. Your bond formed by metal and strong ligand is considered to be covalent, correct? Then we have our octahedral complexes where your central metal cation is either D2sp3, that means if your complex is having hybridization D2sp3, then what is going to happen? Then your complex is going to be inner orbital complex, which means the d orbital will always n minus 1, okay, n minus 1 d orbital, that is one thing. And if the hybridization is sp3d2, that means the complex is going to be outer and the d orbital involved is nd. You will eventually understand when we'll be taking up the examples, okay? So this is the chart that I have told you to see and go through properly in your previous video. Alright, so our very first example that you can see on your screen is potassium ferrocyanide, correct? K4FeCN6. Okay, so before wasting our time, let's proceed further. So as I told you, this is the example and its official name is IUPAC name is potassium ferrocyanide, correct? Ferrocyanide. So earlier in the previous video I have told you that CN act as your strong field ligand, correct? Now what is the first thing that you are required to do over here? Let me just correct the slide, clean the slide first. Okay, so the very first thing that you are going to do over here is you have to calculate the oxidation state of your central metal atom, correct? So your central metal atom over here is this iron, correct? This is your central metal atom. All you have to do is take its oxidation number as you can take as X, and you know on potassium carries +1 charge as it belongs to your first group, okay? And multiply it with 4 as you have 4 potassium over here, plus X minus 1 into 6 because your cyanide carries -1 charge, okay? Then you will get your required oxidation state, that is +2 of iron. In this complex, iron is having +2 oxidation state. I hope you have understood here. So the next part that you are going to do over here, you have to write down first the electronic configuration of your iron atom, correct? Then you have to write down the electronic configuration of the Fe2 plus ion, correct? So By 2 plus, what we understand is that 2 electrons are lost. Okay, and 2 electrons are lost from your this orbital, 4s orbital. Correct? Then you have to write down, you have to fill the electrons in your 3d 4s 4p orbital. Why we have written like that? Because you have to basically check over here. This is your, see, this is your octahedral complex. So the very first postulate that we have read is that your central metal atom should have how many number of vacant orbital should be equal to the vacant orbital should be, number of vacant orbital should be equal to the coordination number. Correct? So see what we have to do over here. This is the electronic configuration of iron atom, and this is of Fe2 plus ion. Then below one, this one. Correct? So how we check whether it is inner and outer orbital complexes? In case of inner orbital complexes, your d orbital involved should be n minus 1d. So if your n value over here is 4, that means it is 4d. Okay. So you can say that if it is nd means it is going to be outer, but we have to check over here. Now I'm just giving the example how you have to see. If n is 4, then n minus 1 is going to be 3d. Correct? So if it is 3d, if your 3d orbital is getting involved, the complex is going to be inner orbital. If 4d orbital now is getting involved, then the complex is going to be outer orbital complex. See, such kind of questions usually may be asked in your subjective papers, just if examiner wants to give you some sort of easy questions related to VBT, he or she can simply ask what are inner and what are outer orbital complexes. Correct? And you have to give an example of each of the two. Right? So yeah, what we are talking about, yes, you have to fill for your Fe2 plus ion, the atomic orbitals over here. Okay, then you have filled it. Yes, as per Hund's rule of maximum multiplicity, you have filled the electrons over here, and as per Pauli's exclusion principle as well. All right, so you can see how many unpaired electrons are present. Since over here 4 unpaired electrons are present. So I've already told you in one of the postulate of your VBT that strong field ligand has the tendency to pair up the electrons. Pair up the electrons. So what can happen over here? This electron will get paired with this. This will get paired with this electron. Correct? Let's see in the next slide. Okay. Alright. So I have mentioned the effect of strong ligand over here. Strong field ligand which cause larger splitting of d orbital and favor the pairing of electrons. Correct? That we have already discussed. So what will happen? It will get paired like this. Correct? Yes, you can see. Just give me a second. Alright. So pairing occur now, and you can see unpaired electron like this. Just give me a minute. This slide is not working properly. Okay. So back to the same question. Okay, so pairing occur now. See how many unpaired, how many empty orbitals are there. We need 6 empty orbitals as per the coordination number. So here we have 2 n minus d orbital, n minus 1 d orbital, 1 s, 1 p, 3p. So how much it is? D2 sp3. So if the hybridization is going to be D2 sp3, I have told you it is going to be inner orbital complex. This is your outer d orbital and this is your inner d orbital. Understanding or not? I hope you have understood it well. Your Cn negative is strong field ligand and it approaches very fast to the metal line. Inner electron are going to, sorry, let me correct it. This is repulsions. Okay. Inner electrons present in the metal ion will be suffering repulsions. Correct. So, due to repulsions experienced by the incoming electrons from the 6 ligands, they will get paired up. That means these electrons will be suffering some sort of repulsion. So these two orbitals will get paired up with the rest of the 2 unpaired electrons in order to minimize repulsions. Correct. So proceeding further, you can see the structure of your potassium ferrocyanide is something like this. You can see, and geometry is, of course, it is going to be octahedral. You can clearly see the coordination number is 6. So you can clearly figure out that the geometry is going to be octahedral. Okay, now how you calculate magnetic moment? See, n is the number of unpaired electron. Okay, and in the previous slide, go and check out. Are there any unpaired electron left now? No, there are no unpaired electron. So n value is going to be 0. Understanding? N value is now 0. So mu, that is your magnetic moment, that is ultimately going to be 0 Bohr magneton. Correct. And ultimately, if there are no unpaired electron present, then the nature of the molecule is going to be diamagnetic. Correct. And yeah, you have to see as over here inner d orbitals are involved, so it is basically your inner orbital complex. See, I'll be taking only one or two examples of your inner orbital complex, and in the next slide we will discuss outer orbital complex in detail, and then we'll be taking the examples related to your coordination number 4 in another slide possibly. So yeah, proceeding further to the another example. So how your examiner can ask question related to the same, they can ask, if you have to explain the diamagnetic nature of any complex like this complex, or they can give complex like this, hexaamine cobalt 3 plus. So you can figure out over here, you can clearly first of all, you have to just calculate the oxidation state. That is one thing. You have to write the electronic configuration. This is just for your easiness. Okay. This is just for your ease, so that you can easily calculate your Bohr, your magnetic moment. You can find out the nature of complex and all. So ultimately, you will be able to understand whether it is inner and outer orbital complexes. That is one thing. All right. So this is a similar example, but over there we have discussed about potassium ferrocyanide. This is your potassium pericyanide, correct? And here your oxidation number of your iron is going to be +3. Rest is same. I want you to practice in your home, and if you are not able to practice, you can check this video. And yeah, this is the answer over here. Go through it wisely, learn properly, and you will be able to understand VBT very, very well. Okay. So if you have any sort of queries, any sort of issues, any questions related to the same, you can mention it in the comment section, and I'll go through it as soon as possible. So yeah, thank you.